In this video, we will discuss equilibrium. So what is equilibrium? Equilibrium is a characteristics of a reversible reaction where system is maximum stable. And to study the equilibrium, we divide it into two parts. One is physical equilibrium and the other is chemical equilibrium. So you can see the glass of water here. There is water and water vapor at the above, and the water level seems to be constant. But the water is converting into the water vapor, and at the same time the water vapor are converting into water. So it means that the rate of vaporization is equal to rate of condensation, and this state is known as equilibrium. So first we discuss chemical equilibrium. So in chemical equilibrium, chemical reaction is must. And what is chemical reaction? Chemical reaction means symbolic representation of any type of chemical changes in terms of reactant and product is known as chemical reaction. And chemical reaction are of four types. First is on the basis of physical state, on the basis of direction, on the basis of heat, and on the basis of speed. So first we discuss on the basis of physical state. First is on the basis of physical state. So on the basis of physical state, one is homogeneous reaction and the other is heterogeneous reaction. Homogeneous reaction and heterogeneous reaction. In homogeneous reaction, all the reactant and product are in same phase. All the reactant and product are in same phase. Example like when nitrogen react with hydrogen, so this forms ammonia. So here all the reactant and product are in same phase. And in heterogeneous reaction, all the reactant and product are in two or more phase. They are in two or more phase. Example like when calcium carbonate is heated, so it breaks into CaO and CO2. So here all the reactant and product are in two or more phase. Then the second is on the basis of direction. On the basis of direction. So on the basis of direction, one is reversible reaction and the other is irreversible reaction. Reversible reaction and the other is irreversible reaction. So in reversible reaction, the reactant can be converted to the product and the product can also be converted back to the reactant is known as reversible reaction. And in irreversible reaction, the reactant can be converted to the product and the product can also be converted, is not converted back to the reactant is known as irreversible reaction. And reversible reaction always attain equilibrium. Always attain equilibrium. And irreversible reaction do not attain equilibrium. They do not attain equilibrium. And reversible reaction never goes to completion. It never goes to completion. And irreversible reaction always goes to completion. They always goes to completion. And generally the reversible reactions are performed in closed container. They are generally performed in closed container, and irreversible reactions are generally performed in open container. They are generally performed in open container. And the reversible reaction proceed in both the direction, forward direction as well as backward direction. Forward as well as backward direction. And irreversible reaction proceed in only one direction, which is forward direction. Forward direction. Then the third is on the basis of heat. So on the basis of heat, one is exothermic reaction and the other is endothermic reaction. Exothermic and endothermic. Exothermic and endothermic. So in exothermic reaction, the heat is evolved, means the heat is released. Heat is released. and in endothermic reaction the heat is absorbed. The heat is absorbed. So in exothermic reaction the heat is released, means when the reactant is converted into product, so some energy is released, and if we suppose that energy is x kilocalorie, so we can represent this by the change in enthalpy, which is delta H, which is equal to the enthalpy of product minus enthalpy of reactant, which is negative. And we can represent this by graph also. So this is the progress of reaction, and this is the enthalpy. Suppose the enthalpy of reactant is this and the enthalpy of product is this. So this is the graph, and this gap is delta H, which is negative. And in endothermic reaction the heat is absorbed. So reactant and some energy is absorbed, which is x kilocalorie, and this forms product, and we can represent this by change in enthalpy, which is delta H, which is equal to the enthalpy of product minus enthalpy of reactant, which is positive. And we can represent this by graph also. So this is the progress of reaction and enthalpy. Suppose the enthalpy of reactant is this and enthalpy of product is this. So this is the graph, and this gap is delta H, which is positive. And in exothermic reaction generally there is bond formation. Example, like when nitrogen react with hydrogen, so this forms ammonia. So there is bond formation, and in endothermic reaction there is bond dissociation. Example, like when calcium carbonate is heated, so it gives CaO and CO2. So there is bond dissociation. Then we talk fourth is on the basis of speed. So on the basis of speed, one is fast reaction and the other is slow reaction. So generally ionic reactions are fast reaction, and generally molecular reactions are slow reaction. Example, like in fast reaction when NaOH and HCl react, so this form NaCl and H2. Means when an acid and base react, so this forms salt and water, which is a neutralization reaction. And in slow reaction, 1 mole, example like 1 mole of hydrogen react with 1 mole of iodine, so this forms 2 moles of HI. And in fast reaction, the rate determination is impossible. And in slow reaction, the rate determination is possible. So now we'll talk about the characteristics of equilibrium. Suppose if we take a container, in this container if we take nitrogen and this react with hydrogen and this forms ammonia. So first we balance this, so the reaction is balanced, and initially at T is equals to 0, we take nitrogen as 10 moles, hydrogen as 30 moles, and ammonia is not formed. So we assume that 1 mole of nitrogen react per second. So at T is equals to 1 second, this will be 9, and 3 moles of hydrogen is reacting, so this will be 27, and 2 moles of ammonia is formed, so this will be 2. So at T is equals to 2 seconds, this will be 8, 24 and 4. And at T is equals to 9 seconds, this will be 1, 3 and 18. So at T is equals to 10 seconds, this will be 0, this will be 0 and this will be 20, where the reaction is completed. So we have taken nitrogen and hydrogen, and these both combine and form the ammonia molecule. And as the reaction proceeds, we see the color change in this. And suppose if we take the volume as 1 liter, and we all know that the moles present in 1 liter of solution is known as molarity, which is represented by capital M, where the concentration of reactant decreases and product increases, and after some time interval we see that the color changes seems to be stopped, but it is proceeding in both the direction. It means they attain equilibrium. So the characteristics of equilibrium is that they are dynamic in nature. Dynamic in nature means, if we talk about an example, when nitrogen react with hydrogen, so this form ammonia. And other reaction like when nitrogen react with the deuterium, so this forms Nd3, and if we mix both these reactions together, so we get Hd, NH2d, Nd2H, these, and this shows that they are dynamic in nature. They are dynamic in nature and they perform the activity at molecule level. Then the second is that rate of forward reaction is equal to rate of backward reaction. We can show this by graph also. So this is rate and time. So this is the rate of forward reaction and this is the rate of backward reaction, and this point is equilibrium, where the rate of forward reaction is equal to rate of backward reaction, and this is our net, which is equal to rate of forward reaction minus rate of backward reaction. Then the third is that the concentration of reactant and product are constant. The concentration of reactant and product are constant. We can show this by graph also. So this is the concentration and this is the time. So the concentration of reactant and product are constant. And the fourth is that color, pressure and refractive index, etc. these are also constant. Then the fifth is that the catalysts do not affect the equilibrium state. The catalysts do not affect the equilibrium state. Even the catalyst shortens the time to attain the equilibrium. The catalyst, it shortens the time to attain equilibrium. We can show this by graph also. So this is rate and time. So you know that this is the rate of forward reaction, rate of backward reaction, and this is the equilibrium, where the rate of forward reaction is equal to rate of backward reaction, and this is in presence of catalyst. The catalyst shortens the time to attain equilibrium. Then the sixth is that we know that equilibrium is a thermodynamic property. It is a thermodynamic property where the Gibbs free energy is minimum. The Gibbs free energy is minimum. We can show this by graph. So this is the graph. So this is the progress of reaction, and this is the Gibbs free energy, and this is the reactant, and this is product, and this point is equilibrium, and here the G is minimum, and this is Gibbs free energy. Then the eighth is that the delta G is equals to 0, and entropy means the randomness, which is maximum, and the potential energy is minimum, where the system is maximum stable. And the 11th point is that the equilibrium can be approached from both sides. From both sides. We can show this by graph also. So this is the concentration and progress of reaction. So the equilibrium can be approached from both the direction. The equilibrium can be approached from both the direction, reactant side or product side. The equilibrium can be approached from both the directions. Thank you.